So to begin with, we're going to be talking about waves entering different media. Media, of course, is the plural of medium. Now this is the reason that transparent objects like glass or ice appear transparent yet visible and not completely invisible. So what is refraction? Well, when a wavefront changes direction as it passes into a different medium, we say that it has been refracted. We can see in this diagram over here, a beam of light is passing into a perspex box and changing direction as it does so. So this is an example of refraction. Refraction occurs whenever a beam of light enters a different medium, regardless of whether or not it changes direction. So this new medium could be glass, or perspex, or plastic, or even the lenses of our eyes. In some special cases, the light will not change direction as it enters the new medium. However, in most cases, it will. And later on, in fact, we'll be looking at the relation between exactly what material the light is passing into and the angle at which it refracts. So this is what a wave looks like when it refracts. We can see that the frequency of the wave doesn't change. The number of wavefronts coming in from the left-hand side of the diagram is equal to the number of wavelengths leaving from the right-hand side of the diagram. We can, however, see that the velocity is changing. In the left side of the diagram, the wave is moving quite quickly. In the right side of the diagram, it's moving quite slowly. Makes sense, right? This yellow line represents the boundary between a fast medium and a slow medium. And because we have, of course, our example, v equals f lambda, we can see that if the velocity of the wave changes, but the frequency stays the same, then the wavelength will also change. And indeed, we can see that the wavelength, that is the distance between two successive wavefronts, is very different on each side of this diagram. Now, when a wave moves into a medium and it slows down, for example, this wave, which is moving from left to right, then how will its wavelength and velocity change? Well, its velocity will decrease, of course, because it's entering a medium that's slowing it down. And that means that, as we can see, its wavelength will also decrease. The wavefronts here are much closer together than when the wave is in the fast medium. So what if we went the other way? What if we had a wave moving from a slow medium into a fast medium? Well, in that case, we just get the opposite effect, wouldn't we? We'd get the velocity increasing and the wavelength increasing. So if we have a barrier that, instead of being completely flat, is a little bit bent, we can actually see why the wave will sometimes change direction. That's illustrated by this diagram over here. When the bottom part of this wave reaches the barrier, it suddenly speeds up. But the top half of the wave is still moving at its original speed, right? So that means that the top half of the wave is still moving slowly, but the bottom half of the wave is moving quickly. And because the wavelength isn't going to get shorter or break apart or anything like that, the whole wave sort of gets dragged upwards like this. And we can see that it's changing direction. And so we can see that the wave as a whole will start to bend. And if in fact we were to draw a ray through these wavefronts, what would that look like? Remember that a ray is always perpendicular to the wavefronts. So it would look something like this. We can see that the wave is changing direction as it enters the new medium. And that's why refracted light will change direction. Now, when a wave enters a medium in which it moves slower, we can see from the diagram previously that it will bend towards the normal. Remember that if we have a surface and light is being shone onto it, then the normal to this surface is simply going to be a line at right angles. We've learned about this before, but don't forget it. So when it enters a medium in which it moves slower, it will bend toward the normal, which means that the angle here will decrease once it's going through the new material. And we can see that in this photograph. So what will happen if it's exiting the slow material and going back into a faster material, like air. Well, you can see what happens from this photograph over here. The wave will in fact speed up and then bend away from the normal. So it means that when the light first passes into the perspex blocks, it'll get closer to the normal, and when it exits, it'll get further away from the normal. And in fact, the angle of the light when it's first in air, as long as the block is rectangular, will be exactly the same as the angle when it leaves. Of course, this will only hold true if the top of the perspex block and the bottom of the perspex block are parallel. If we had a curved surface, then it would be exiting at a normal and bending away from a normal that is quite different to the normal at which it entered. Now, when light moves into a denser medium, like glass or water, it tends to move more slowly than when it's in, for example, air. And similarly, when a beam of light goes from air into water, it'll slow down. Can you remember what this means for the angle? Well, you can see it from the diagram here, can't you? It will bend towards the normal. So that means that the angle of refraction, that is this R at the bottom, will be smaller than the angle of incidence, because we're bending towards the normal. So this means that the light will bend as it enters the water. Of course, if we look at an object underwater, our eyes and our brain don't really get that the light is bending, because they're always used to light traveling in straight lines. And what this means is that we get a bit of an optical illusion. So if we have an object underneath the surface of the water, then the light coming up from it will bend like this. It will refract as it passes from the water into the air. But our eyes don't realize this. They say we're receiving the light at this angle, therefore it must have come from an object that's over here. So our eyes and our brain think that the object is over here when its true location is a bit further down. This is an optical illusion caused by how our eyes perceive light as it refracts. And in fact, if you look at straw that's been put into a glass of water, we can see exactly this illusion. We can see that if a straw is half submerged in water, our eyes see the refracted light, but assume that the refracted light has traveled in a straight line. And it means that the straw seems bent, even though it is of course completely straight. What's bending is the light coming from the straw and tricking our eyes into thinking that the straw is in a position where it isn't. This means that underwater objects appear to be displaced from where they actually are.